uh, who have joined this webinar. Dr. Usha Madam is there. Welcome to you, Madam. Usha Madam, Sudha Madam, then uh, Dr. Mallesh Sir, then Yashoda Madam, Dr. Girija. Many experts have joined. Welcome to Dr. Anant Nayak is also there. Welcome to you all, and also students who joined from different universities of Karnataka and elsewhere. And I also welcome Dr. Srinath, must have joined on YouTube like yesterday. Before starting the webinar, let me give a brief overview of achievements of Dr. Akshata Shenoy. Dr. Akshata Shenoy has completed her PhD from the prestigious Indian Institute of Science, Bangalore. She is the recipient of CIS Government Excellence Postdoctoral Fellowship for pursuing her postdoctoral studies in quantum cryptography at the University of Geneva in Switzerland. Furthermore, she has also conducted postdoctoral research at the University of Bangalore and International Center for Theory of Quantum Technologies, University of Gdansk, Poland. Currently, she is a senior researcher at the center working on topics related to quantum cryptography, quantum correlations, and applications of machine learning. He is also collaborating with industry to benchmark various aspects of quantum technologies. And I'm very happy to inform you that he is also a member of PhD expert. Suraj
Unmute ಮಾಡಿ ಸರಿ. Sorry for the inconvenience.
I am very happy to inform you that Akshata has been a very active person in the group of experts. Today she will be speaking on quantum cryptography. I'm sure all of you will be highly benefited. And if you have any queries or questions, you can keep ready at the end of the talk. You may ask Madam for any clarifications. We'll be happy to answer. With this brief introduction, I request Dr. Akshata to deliver her talk. Over to you, Dr.
Thank you, Professor Ramesh. Thank you, Team KSTA, for inviting me to actually give this talk. And I really appreciate your commendable efforts to bring quantum science and technology here in Karnataka, especially doing this outreach kind of a thing so that it even reaches the general public. So really commendable efforts. Now I would like to, I think the host has to enable me to share the screen. Could you please do it?
Yes, please check now.
Okay. Okay, can you see my screen now?
Yes, ma'am.
Ah, okay, great. Right. So today I'm going to speak about quantum cryptography. I'm kind of trying to give you a basic of cryptography so that in case you want to work in this field, contribute, or just sail through, it should be like easy for you to pick up from where I stop today. Yeah, so the contents of my talk are as follows. So I'm going to give you a little bit of background, then principle behind security, how different it is from classical cryptography, then the first protocol, which is I think the most important protocol in cryptography and the most used, most cited, and most also experimented. Then eavesdropping strategies or cryptanalysis or hacking strategies where a third unwanted party is trying to get knowledge of what you are doing. And then evolution of protocols, some current trends and realizations and conclusions. If you have some questions, please feel free to ask me at the end. And I have tried to put as many as references throughout my talk, but if there is something else that you need, please feel free to write to me. But otherwise, for quantum cryptography, there is a lot of material on the internet. There are a lot of books, and you can pick any one of them. Pretty much they tell you the same things, but from a different perspective. So to begin with, what is cryptography? Cryptography enables two distant parties to communicate securely so that any third party who is not a part of this communication should not be able to access this secret communication that is happening between two parties. For example, here, let's name them Alice and Bob. These are our two legitimate parties who are going to communicate with each other securely throughout my presentation here. Now, classical cryptography is information theoretically secure. Okay, that means it is protected by mathematically hard functions which are hard to compute. Classical cryptography can be like divided broadly into symmetric and asymmetric systems. In asymmetric system, the key that is used by Alice to encode or encrypt or hide her message is not the same as the one that is used by Bob to decrypt. Symmetric systems, on the other hand, use the same key for encryption and decryption. Please note that in the first talk by Professor Usha, she mentioned that asymmetric crypto systems are vulnerable if one day we are going to have a quantum computer, because mathematically hard problems will then be easily solvable and one could easily do cryptanalysis of asymmetric crypto systems. So what is the solution? In this case, one would then have to resort to symmetric crypto systems, where a sender Alice encrypts her message M and there is a secret key where they do a bitwise addition modulo 2, and finally you end up with an encrypted message also known as the ciphertext. This ciphertext is then transmitted over classical channel or the public channel, and Bob receives it, who can decode it using the same key. This is the key difference between asymmetric and symmetric. Now note one thing, that for Alice and Bob to follow symmetric, they have to use the same key. But note that this key has to be as long as the message itself. So one should find way for Alice and Bob to share this key somehow. Okay, it's not possible for them to meet every time that and share a key so that in future they can exchange some secret message. So one has to find some convenient way of distributing keys. So the most known like symmetric secure system is this one-time pad, where you use a symmetric crypto system and you use the key only once. Okay. So as a solution to quantum computers, we are going to use symmetric crypto systems because asymmetric ones are vulnerable. Now to give you an example of how symmetric crypto systems kind of need to work, for those of you who have a pen and a paper, you can try doing this at home now. Consider a message M. This is a 8-bit string. Consider another key K, okay, and now try to do bitwise addition modulo 2. For example, if you have 1 and 0, it should be 1. Note that if it is 1 and 1, it should just be a 0, okay? Please don't carry 1 to the next column. So finally, you should end up with an encrypted message. And if you do the reverse, that is, take this encrypted bit string, add the key again, you should be able to recover your original message. So you have done encryption and decryption this way. Now consider this message M. So keep it aside. Consider another message capital M. Okay. Take this same key K and try to do M addition modulo K. Okay, and obtain an encrypted message capital E. Now I would like you, if not now, maybe at a later point, try to do addition modulo of this small m and this capital M. Also try to do addition modulo 2 of this encrypted message E and this encrypted message E. Note that you have used the same key for encrypting both of them. So now compare these two. You should be able to obtain the same bit string for both of them, for both the addition modulo 2 of the original message and the encrypted message. So this shows that the repeated use of key makes your symmetric crypto systems vulnerable. So what are the key takeaways from this if one has to use symmetric crypto systems? Your key should be secret, because that is how your security comes from. the length of your key should be as long as the message itself. This is a problem because one then needs to distribute huge length of keys. The key should be truly random, okay, because secrecy also relies on that. By truly random, I mean that if you pick any one bit from your bit string, you should not be able to predict any other bit from the bit string, okay. So we are going to discuss a little bit more about this at a later point in the talk. Now, the key should only be used once, like we saw in the earlier example. So as a solution to this distributing of keys for symmetric crypto systems, you have quantum key distribution. So quantum key distribution is just one part of cryptography, which enables like two distant parties to share a secure random bit string. But here security comes from laws of quantum mechanics, unlike classical cryptography. There are other tasks as well within quantum cryptography, which we are not going to touch upon today. But if you follow my talk today regarding key distribution, you should pretty much be able to catch up on these things. So one of them is secret sharing, where a secret message can be shared among several of the parties and one of the chosen party can recover it at a later point of time. Secure direct communication, where direct messages can be sent to the intended party. And then there is bit commitment, which is mostly like used in gaming. So I know for the past 2 days, like most of the audience have been like very interested in the no cloring theorem. So no cloring theorem is one of the physical principles which gives you security in quantum cryptography. So we are going to look at it a little more detailed compared to what the other speakers have already told you about it, because it's very crucial for you to understand this part of the security, and then you can sort of build on the intuition that you gain from this, okay. So the no cloning theorem was proposed by Wouters and Jurek in 1982. Please note the year, because later we are going to compare it with other events that happened with respect to quantum cryptography. So the statement of no cloning theorem is that any arbitrary quantum state cannot be cloned perfectly, okay. Any arbitrary or any unknown quantum state. It is impossible to build a universal quantum copier. What do I mean by that? You have your photocopy machine. This is a universal photocopy machine. By that I mean that take a document, it doesn't matter what are the contents of the document, what language the document is in. Irrespective of that, your photocopy machine is going to copy it onto a blank paper. But quantum mechanics prevents one from having such a photocopy machine or such a quantum copier. So the first part of this proof for no cloning, we are going to prove it by linearity of quantum mechanics, okay. So we start the proof by assuming that, let us assume that it is possible for you to have a universal quantum copier, okay. Now consider an arbitrary quantum state, okay, which is a continuous superposition of 0 and 1. For those of the students who are not familiar with these notations, don't worry, here the ket 0 just represents, you can imagine it to be representing polarization state of a photon, for example up state and the down state, okay. Just assume that there is an arbitrary quantum state now and you have a quantum copier. So if there exists a quantum copier, what should it do? So this quantum copier, which I name as USB, should now act on this state which you want to copy, and this is your blank paper P onto which the copying should happen, okay. So this U should act on the joint states of this, and finally your original state should remain undisturbed, and then also a copying should happen, okay. Now, a quantum copier should copy the state irrespective of it. Like I gave you this example for the classical copier machine. Whatever is your document, whatever language it is in, whatever other contents, it should copy. Okay. So now, once you acted your copier on the quantum state, this is what you get. Psi and psi, you should get a perfectly cloned state. Now, just substitute for psi here from the previous question, and this is what you get, okay. Now by linearity of quantum mechanics, here in this equation, instead of just writing USB this, directly now substitute for psi. Okay, earlier we have not. This is also valid. So just write USB and then expand it alpha 0 plus beta, and then you have your blank paper. Now if you write it in this fashion, your quantum copier is going to copy it differently. Look, observe that 1 and 2 are not equal, they are different. This should not happen. So if there is a universal quantum copier, how it copies, what it copies should not depend on how you write your states or how your underlying states are. Thus, we prove that linearity prevents you from having a universal quantum copier. Okay, so there are some references at the end of each slide, like I have referred to here Mark Wilt's book, but there is also Nielsen and Chuang, there is also Preskill notes which gives you a very good introduction of these things. And for students to understand it better, just in this part, you can substitute. For example, take the state 0, the up state, and the blank paper, and then see what happens. Similarly, the down state, and then it should be able to copy. And then take, for example, elliptical polarization, a blank copy, and what happens, and substitute here, like expand this in terms of linear polarization or the Z basis, which we will see later, and then you see that these two are not equal, just for you to understand intuitively how no cloning works. Okay, now we see another proof of no cloning theorem. This is proof by unitarity. Again, let's assume that there exists a unitary operator U which acts as a universal quantum copier. Okay, by definition, U are some special matrices, let's say within quantum mechanics. If I and U is said to be unitary if it satisfies this definition, where U dagger is nothing but the conjugate transpose of U. So if you have a matrix U, conjugate it and transpose it. So U dagger U should be equal to U dagger, that should be equal to the identity operator. Okay. Now consider two arbitrary quantum states, okay, psi and phi. Okay, there are two different states which can again be expanded as before, alpha 0 plus beta 1. Now we want to copy these states by using a universal cloner U. So let U now act on this state psi and your blank paper to give you clone copy like this, and similarly on psi to give you a cloned copy like this. Okay, now take the inner product of 1 and 2. Inner product, for those of you who don't know, think of it as a generalized dot product. Okay, so you take conjugate transpose of this and you write here, and then this part is written here. So what you get is inner product of psi with phi, and then psi with phi mod square. What does this mean? It means that it is possible for you to copy states if psi is equal to phi, or if they are orthogonal to each other. So for those of you who ask these questions about distinguishing states, state discrimination and cloning, so it's possible for you to copy two quantum states if they are the same or if they are orthogonal to each other, then they are perfectly distinguishable. If they are not orthogonal to each other, then copying them perfectly is not possible. Okay, so this is proof by unitarity that a universal quantum copier does not exist. Think about it, ponder about it later, and also probably I think there will be the recording of this on YouTube. Go back and then try to solve these examples and think about it. So yeah, so just to give you an example, you see here 0 and 1 are orthogonal to each other, so they can be cloned. And here you see this 0 and plus, they are not orthogonal to each other, so there is an overlap of 1 over root 2. Okay, so these, if these two states are transmitting along the channel, for example, then one cannot distinguish them or perfectly clone them. So for those of you who are interested in further reading or investigating these things and trying to understand what are the physical systems where optimal cloning can be observed, these are some references which I enjoyed reading as a student. Some of them are very easy to read, some of them are not, but I think you can still get intuition of what is happening with respect to cloning from these articles. Now, the second point which gives security in any cryptographic protocol, especially in prepare and measure protocols, we will see what they are later, are the use of mutually unbiased bases or conjugate bases for encoding. By mutually unbiased, I mean that, see here you have the 0 state and plus state, that is a linear polarization, elliptical polarization. There is an overlap of 1 over root 2, okay. So these are states from the mutually unbiased bases. How? So I introduced to you what is known as computational basis or rectilinear basis or Z basis. When one talks about quantum information, they all mean the same. So in terms of polarization, they are the up and the down polarization. They are integrated by Ket0 and Ket1, okay, and sometimes very commonly by this in cryptography. And then the other basis which is used for encoding your photonic states are Hadamard basis, diagonal basis, X basis. They all mean the same. This is just to introduce the notations again in terms of polarization and states, and this is how it is represented. So why are they called mutually unbiased bases? If you take one state from one of the bases and take an inner product with either one of them, you are going to get an overlap of 1 over root 2. This is true even if you take one and then take overlap. So each of the states from one basis will have equal overlap with each of the states in the other basis. So this is a definition for mutually unbiased bases, and they are very useful in quantum cryptography, because if you use these this kind of encoding for your photonic states, then as you know there is an overlap. They are not orthogonal, and any person who wants to read them or distinguish them cannot do it perfectly, okay, thus protecting the secrecy of your protocol. So to expand a little bit more on what happens when you encode your photonic states using these bases, assume that you have prepared your quantum state in the Z basis and you measure the state by putting into a measurement device, measure it in the same Z basis, okay. You should be able to recover the same state, okay. Now, if you prepare a state in the Z basis and use, for example, X basis, okay, a different basis to measure, then you are going to disturb the state. So with 50% probability, you should either get 0 or 1, okay. You are not going to recover the original state in which the photon was prepared. This is true, like even if you take a state in X basis and measure in the same basis, you should be able to recover. And again, basis mismatch, you should not be able to recover, you are going to disturb the state, okay. So measurement in same basis does not disturb the state, so states can be inferred exactly. Measurement in different basis disturbs the state, and then there's no way for you to know what was the original encoding of this state, okay. In one sense, this can be looked up as a manifestation of uncertainty principle. There is one more basis for qubits. Look, throughout this talk, we are only going to consider two-level systems or qubit, okay. So for qubit, there are three MUBs, X, Z, and Y. In terms of polarization, elliptical, circular, and linear, okay. So this is the Y basis, and there is subscript Y to indicate that. So these basis states are non-orthogonal, like I mentioned, and each one of the basis states can be represented in terms of the other basis states, okay. For example, 0 can be represented in terms of the X state, and here the X basis states can be represented in terms of the Z, okay. So for terminology sake, this is also known as conjugate coding, encoding using basis states. And people also mention information versus disturbance. By that they mean that if you prepare a state in one basis and you try to gain information about that state by measuring in a different basis, you are going to disturb the state. So the act of you trying to gain information of this state by making measurement in a different basis is going to disturb it, okay. This is the meaning of information versus disturbance trade-off. So these are the main principles for now, for today. There are some more, we are not going to touch upon that. So no cloning, MUBs, information versus disturbance. This should be enough for us for today to sail through this talk. Okay. Yes. Now we come to the first simple, creative, and most beautiful idea of quantum information. Like some of my postdoc supervisor, he even mentioned that if you look back, we wonder why this idea was not proposed much better. And he even thinks that if a college student or a school student was aware of quantum mechanics at that time, maybe the proposal of quantum cryptography would have come from young minds. Okay. Yeah. So now this is the first application of quantum information that we know today, but unfortunately there are some unfortunate things attached to this, so let me tell you. So Stephen Wiesner was in Columbia University, and in the around 1969 he proposed, or he put up his idea about conjugate coding, where for the first time he points out that there are quantum systems which can be used for coding with respect to communication, and they can provide you security which is much different from classical communication, and the quantum states cannot be copied is also what he says in 1969, okay, in this paper. But note that the no cloning theorem was published and proved in 1982. This is because when Stephen Weisner sent his this paper to IEEE, it was rejected. So there is some debate that this was rejected 15 times and this was rejected once. I am not sure, I mean people are not sure which one is what, but for sure it was rejected, and Stephen Weisner was very disappointed, because this paper really contained a lot of things like quantum money, the idea of quantum encoding, and QRAX, what yesterday's speaker HS Karthik was explaining, and also the no cloning theorem. So he was very disappointed. Stephen Weisner gave up academia. He left US, went to Israel, and then he was involved actually in construction work because he thought that this is good for his soul. So he totally gave up academia. He was disappointed at that time. But I think later somehow they tried to publish this paper and it appeared in 1983 in ACM. So this is just a tribute to Stephen Weisner, who really gave amazing idea in 1969 with this seminal paper. So I've taken this picture from Scott Aronson's blog, so where he lists like what the paper says, that this is the first paper which spoke about cryptographic security, no cloning theorem, even though it was only coined in 1982, and the first protocol of quantum cryptography, which we are going to look in a minute, the BB84 protocol proposed by Charles Bennett and Gilles Brassard. Actually, it is one of the most cited paper, like I said, and they also won the Wolf Prize for this, which is on next to Nobel Prize. But Stephen Weisner was not acknowledged in this, but the forefathers of quantum information or quantum cryptography have always acknowledged him throughout their talks and in various forms. But Stephen Weisner's effort was recognized in 2019 by the Chinese government in the form of the Mises Quantum Prize. So all the three of them, like Stephen Weisner, Charles Bennett, and Gilles Brassard for BB84, and Arthur Eckert for his entanglement-based quantum key distribution protocol, which we are going to briefly touch upon. All of them were awarded and recognized. Okay, so now let us look at the first protocol, which you can say is a reformulation of Stephen Weisner's 1969 article or paper. And as I repeat myself, it's really one of the most cited paper, and if you understand this protocol very well, then it's quite easy for you to sail through all the other protocols within quantum cryptography. That's the kind of intuition it gives you. So BB84 was proposed, interestingly, in Bangalore, There was an IEEE conference which was being conducted by the Indian Institute of Science, so which is known as International Conference on Computers, Systems and Signal Processing. So this is the cover of this which I have from IAC archives. So I'm told by Charlie Bennett that this conference took place in, I think, the Hotel Lalit, which was known as Lalit Ashok before. So some of you might know this because I think the Bangalore Nano Conference also happens here. Yeah, so the protocol was made known to the public or proposed first time at this conference. So let's now understand the details of the BB84 protocol itself. So there is our legitimate party, Alice and Bob. They have access now to quantum channel by which they are going to do the quantum key distribution protocol. Okay, so they are going to share a key which is at a later point they may use it to share a secret message. Let's say by using symmetric crypto systems. Some of the assumptions that go behind a quantum cryptography protocol are these, like in general, okay, this is in general for any quantum cryptography protocol, that quantum theory is a valid theory. Alice and Bob are in a secure station or laboratory. Look, it doesn't make any sense that if there is an eavesdropper or some malicious agent sitting inside your own laboratory, right, then there is no security. He's just snooping by sitting inside your laboratory. Both of them should have access to trusted source of random number generators. You will understand this better why subsequently now. Alice and Bob are connected through an authenticated classical or a public channel. Okay, now in addition to a quantum channel, Alice and Bob should first authenticate themselves. By authenticate, I mean they should verify or ascertain their identity by using a classical channel. It could be like your email, your telephone, mobile phone. You know that this number is attached to this person, and there could be some authenticator like a password or something, or some kind of identification verification protocol. Okay, both of them should have access to a quantum channel. Now this quantum channel can be untrusted. By that I mean there can be somebody stooping over this quantum channel. This person also could make some changes in the quantum channel or do some operations. But with respect to the authenticated classical channel, the stooper, or whom we known as Eve, she can listen but she cannot make any changes, okay, over the classical channel. Alice and Bob now also trust their devices used for state preparation and measurement. Now this comes because, look, every time Alice and Bob want to communicate with each other, they cannot build their own devices. They have to buy it from some vendor or from some agent, from some company. So now these devices have to behave as they are promised, okay, according to their manufacturer's sheet. Now, if the device seller itself is a Eve, then what happens? This is another consideration. But for now, we assume that Alice and Bob trust all their devices used for state preparation measurement. And below here is a reference of which is a reprint of this BB84 protocol. I think this is more accessible and in a more readable form if someone wants to kind of read it. Okay, a little bit more about random number generator because this is very crucial. This dictates the security aspects of your protocol. Quantum random number generator can be a simplest form of it can be a 50-50 beam splitter where the reflectance and the transmittance coefficients are like half. Now, random number generator via quantum effects or quantum processes are the only true sources. Ideally, looking at the bit sequences generated by quantum random number generators, you should not be able to like recognize any patterns. But any other like program, a computer program that you write, they are pseudo random. They are not true random. That is, after a certain sequence they could start repeating themselves, or you can identify some patterns. So here is an example of a pseudo random number generator which is available on the internet in this web page. You can check out because I think there are huge bits available. And quantum random number generators have been commercialized. They are available. So I give you like two examples which are offshoots, like startups from two universities, like University of Geneva where I did my postdoc, and this is secure from the current group where HS Karthik is actually working. So his PI is a part, one of the owners of this company, and here I think they have a beam splitter, and here they have some source. They fire it. This is a fan for cooling, and here this part I have seen this device. So this part is it provides Wi-Fi. You can even have some kind of LAN cable connected to it, and so this device actually provides you quantum safe Wi-Fi. So I was able to see this like at a small scale. These are commercially available and can be bought. And in India, you have QNew Labs, which has got quite a good amount of attention internationally. They too have quantum random number generators as one of their projects. Now let us go into the details of BB84 protocol. So here on the left side, you have our Alice. She has a source which prepares quantum states, and these are devices used for her preparation. She has access to a quantum random number generator, which is randomly outputting 0 or 1, and let her assign 0 to Z basis. Okay, so whenever her random number generator outputs 0, she presses Z basis in her preparation device, and to 1 let her assign X basis. Okay, similarly she has this telephone line which she is going to use as a classical channel for both authentication and then at a later stage for basis reconciliation, which we will understand a little more. So Alice prepares her photonic states randomly by selecting basis depending on her random number generator output. Now on the right side you have Bob, who has similar devices to Alice, but his job is only to measure incoming photons randomly by using his quantum random number generator, which is locally present in his lab. Okay, the random number generator of Alice and Bob, they are independent. They should not be correlated in any way. They should act independently. They should give bit values independent of each other. Now both of them are connected by a quantum channel on which your photonic states are transmitting. Let's not get into the detail of what is quantum channel for this talk, but just think that if you input a quantum state into a quantum channel, it should like faithfully give you a valid state at Bob's end. Okay. Sorry. Hello. Okay. For more details, I again recommend Nielsen and Chuang. Right. Now let us see how the actual protocol happens. Okay. Look, so these protocols like BB84, where Alice prepares photonic states in certain bases, transmits them over a quantum channel, and Bob measures them, are known as prepare and measure protocols. Okay. Now imagine that Alice has a random bit string. This could be classically generated. Okay, it doesn't matter. Now let's say she has like 0 1 1 0 1. Now these are Alice's bases, which she is going to choose based on the output of her random number generator. Okay, so if a random number generator output 0, she is going to press Z. Now if she has pressed Z, look, her classical bit string here is 0. So corresponding to that, in the Z basis, she is going to prepare get 0 or the up state. Okay, if her random number generator outputs 1, she is going to press the X button for her preparation, and corresponding to this 1 classical bit, she is going to prepare the state -1. Okay, so this is how she like sends a huge amount of photonic states to Bob along the quantum transmission channel. Now the source which prepares these photons are spontaneous down converted sources or single photon sources sometimes, and the quantum transmission can happen in quantum channel, which for you to imagine, it could be your fiber optic cable, for example, and then the preparation and the measurement devices are optical elements, and on the measurement side you also have single photon detectors. Okay, now all these states are photonic states which are now transmitted over the quantum channel. Now Bob on his end receives these photons. Okay, he has his random number generator which is inputting classical bit values randomly, zeros and ones. So based on that, if his quantum number generator has output 0, he also presses the Z button, just like Alice. Okay, and look here that Alice has prepared the state in the Z basis. Bob is also measuring the state in the Z basis. Their two random number generators are independent, they are acting independently. But because these two states were prepared and measured in the same basis, Bob should recover the original classical bit, okay, 0. So this is your raw key, okay. Bob just notes it down. Now look in the second column, Alice and Bob have measured in the different bases. We know that when two states are prepared and measured, when a state is prepared and measured in a different basis, you are going to disturb it. For sure, you are not going to recover the original encoding. Yes. So here with equal probability, you can either get 0 or 1. So whatever Bob gets, he just records it. Okay. And here also he just records it. So here both of them have measured in the same basis, and in the last column also the same basis. So both the classical strings of Alice and Bob are correlated. Now the raw key that is generated at the end of the transmission is recorded by Bob, but there are errors in it because in some cases they have measured and prepared in the same basis, in some cases they have not. So now one needs to reconcile or make both the keys as close as possible to each other, because they have to use it for communication at the later date. And if they have to use symmetric systems, both these keys have to be identical. So as much as possible, they need to reduce the errors. Look here, this is ideal transmission that we have considered. Okay, no noise, no Eve who is creating some disturbance. So in this case, the raw key itself should be your not the raw key, the shifted key, which we will see now, should be your final key. So what do I mean by that? So once Bob measures, records his outcomes, both Alice and Bob come over a public channel to do what is known as basis reconciliation. They pick up their phones, okay, and now Alice over this phone call is just going to declare the basis of her measurements, not the outcomes, okay, not these outcomes, just the basis. And Bob is also going to declare his basis. So the cases where both of them measured in the same basis, they are going to retain, and the cases where they measured in different bases, they are going to discard. Okay, so this process is basis reconciliation, and the shorter key that is retained, which is the correlated key for Alice and Bob, is known as the shifted key. So only 50% of the original bit string survives after this process, because you see the probability which Bob makes the correct measurement and the wrong measurement is half. So in an ideal scenario, in the absence of noise, the shifted key itself is your final key. Okay. Some points to remember. Alice and Bob do not have control over what is the final key. Okay. Their joint actions is going to lead to the final secret key. Quantum random number generators are independent, and in any quantum cryptographic protocol there is quantum transmission, but there are also classical post processing and classical authentication. So these are classical protocols. So a quantum cryptographic protocol will necessarily contain classical processes also. Now let us consider realistic scenario or eavesdropping. Okay, so Eve is by definition malicious. She is going to attack channel, because in quantum cryptography the idea is that once key distribution is done, and if Eve doesn't attack the quantum channel, there is no way that she is going to have some knowledge or gain knowledge of the bit string shared between Alice and Bob. So she has to attack the channel when the protocol is taking place. This is unlike like classical communication. Classical communication would want an Eve, for example, not to cryptanalyze your protocol, but here we are not preventing Eve from attacking, or not preventing Eve from hacking or cryptanalyzing. We want her to attack, and we are sure that we are protected by the laws of quantum mechanics, and her presence is always going to be detected. So some things which we should keep in mind about Eve is that Eve has access to all the sophisticated technologies. She could be much more powerful than Alice and Bob. Her presence on the quantum channel manifests as errors. Okay, whatever operation she does on the quantum channel should show up as error. Okay, because the most simplest thing that she can do is what Bob does. She can also measure randomly in X or Z basis, and sometimes she's going to measure in the right basis and have information on the key. And the cases where she makes measurement in the wrong basis, she has information, but she is also going to add error to this key. Okay, she has no access to Alice and Bob stations. Quantum channel is untrusted and could be in her control. So like I mentioned, she can only listen to classical communication but not modify it. So her aim is to gain knowledge about the shared key between Alice and Bob without being caught, and she is forced to attack when the protocol is happening. So the simplest strategy that I mentioned that she could do is just be on the quantum channel and do the same operations that Bob does. Okay, this is known as intercept and resend attack. So Alice prepares her states in the X and the Z basis. She puts it on the quantum channel for transmission. So now Eve has control of the quantum channel. She measures just like Bob. She has her own local random number generator, quantum random number generator, and based on the output she measures, she records her outcome. Okay, and based on whatever is the value of bit value of her outcome, she prepares her corresponding photonic states and forwards to Bob. Okay, so here no cloning theorem prevents her distinguishing from these states. Remember that we have used mutually unbiased or non-orthogonal states. So there is no way she can copy. She has to measure. Okay, if she has to gain information, she has to measure, and in the process she is going to disturb them. So let's look at the same table now, but with Eve's attack. Okay, in the first column, see that Alice has prepared her state in the Z basis, and you have the 0 up state. Let's say that Eve also by chance measures the incoming photons in the same basis, in which case she has to obtain the same outcome as Alice, and she prepares the correct state and forwards it to Bob. Now assume that Bob also has measured in the same basis. Okay, now in this case Eve's presence here on the channel is not caught because she has measured in the same basis as Alice and forwarded the correct state to Bob, who has also measured in the same basis, obtains the correct outcome. And when they go for basis reconciliation over telephone, Alice declares that, hey, I have prepared my state in the Z basis. Bob says, I have also measured my state in the Z basis, and they decide to keep it. So Eve has information on their key and they don't know her presence. So this is some kind of information leakage about the secret key. Okay. Now the cases where Eve measures in the wrong basis compared to Alice, she measures the wrong state, and the cases where Bob and Alice measured in different bases, they are anyway going to discard, so it doesn't help Eve. In this case also you see that Alice and Eve have measured in the same basis, so Eve prepares correct states, forwards the correct state, but Bob has measured in a different basis. So Alice and Bob, when they do basis reconciliation, they see that okay, there is a basis mismatch, they anyway discard it. So this is also not going to help Eve. Now this is the case where all of them have measured in the same basis, so Eve has information, so this is leakage. But look here, in this case Alice has prepared a state in the X basis, Bob has made a wrong measurement, so with equal probability he will send either the 0 or the 1 state, that is a probability of sending a wrong state is there. But observe that during basis reconciliation Alice announces X basis and Bob also announces X basis, so both of them have measured in the same basis, so they think that their key is correlated and Bob just records whatever he has. So there is a possibility that Bob records a wrong bit here. Okay, because with equal probability he may get either 0 or 1, so there is a finite probability that Bob records a wrong bit value. Instead of 1 he can record 0. Okay, now this is for students. If you want to go and work this out for yourself, I have just prepared this example. You can probably even take a snapshot now or look it up later on YouTube and then try to solve this for yourself so that you can understand it better. So what are signatures of Eve when you run a quantum cryptographic protocol? Eve's attack appears as errors on the shifted key. We assume when we analyze the security of a protocol, we assume that all errors in the key are introduced by her. Alice and Bob do not have perfectly correlated key, so they have to do something by which they make their key more and more close to each other or correlated. So for intercept and recent attack, about 25% of error is added on the shifted key, and information leakage is also there, and sometimes Alice and Bob may not realize this. So this is one of the very, very basic and simple attacks that I told you just for demonstration purposes, but there are like very complex attacks, individual attacks, coherent attacks, and collective attacks, which one needs to consider when talking about security of a quantum cryptography protocol. Then there are other attacks which are physical attacks, which come across not because of theory but because of practical implementation, or the way these protocols are realized because of some characteristics, limitations of the platforms, like characteristics of the fiber optic or the detector. So these are photon number splitting, detector blinding, side channels. So I have given you a lot of references, but really there are a good amount of review articles on quantum cryptography. Please pick them, and there is a lot of information. Please go ahead and read them. So finally, like I said, Eve has added error, and as well as she has some information on Alice's and Bob key. So we have to estimate the error, and then we have to also know her error rate, that is her information on the correlated key between Alice and Bob. And they also have to, Alice and Bob have to amplify their correlation between their key. And so positive key rate in this case can be defined when Alice and Bob are more and more correlated than Alice and Eve's key or Bob's and Eve's key. So only in case where Alice and Bob are more and more correlated, secret key distillation is possible. So this is known as the Shizar-Kerner-Brown. There are standard classical protocols for you to do post-processing. This itself is a topic for another talk, so I will not go into the details, but you can look them up. So just to give you a quick overview of what other protocols exist in quantum cryptography. So there are variants of BB84. So far what you have seen is polarization encoding, where you're using the X and the Z bases for encoding, but there is phase encoding, where phase between the two arms can be used for encoding. So this is one other protocol. And then there is the 6-state protocol, where all the 3 basis states of a qubit can be used for encoding. This has some advantages in terms of eavesdropping. So you can look up this paper by Dagmar Bruce if you wish to. And I think the previous 2 speakers have already introduced to the concept of Bell inequality or CHSH inequality. So there is this protocol known as the Eckert protocol, which uses this. So the basic idea is that if Alice and Bob are sharing an entangled state, then they can make some measurements at their end, analogous to measuring X and Z bases in the BB84 protocol. In addition, they also check for CHSH inequality. And if they observe that a CHSH inequality is violated, this ensures security. Okay, so this is a different form of protocol. This is not a prepare and measure protocol, but these are entanglement based protocols where security comes from violation of Bell inequality. Okay, up to 2 root 2. 2 root 2 says that the correlation share between Alice and Bob are definitely quantum, and they are not correlated to any third party. If in case Eve tries to attach a probe and then try to gain information about what correlation Alice and Bob share, then this 2 root 2 bound is going to reduce, okay, showing her presence. So this is a different form of security. We don't go into the details here, but this paper is very simple to read, the Eckert 91 paper. I totally recommend it. I think anybody can easily get it. Okay, some current developments and considerations, just to give you like an idea of what is happening in the field. So one important thing that is happening currently is this device independence, where you relax the condition that the devices used for state preparation and measurement are trusted. So you can buy your devices used for preparation and measurement from a third party, a vendor, even Eve. Okay, she can place something inside this device which can track what exactly you are doing and compromise the security. So how are you going to rework your security in this case? Is device independence considerations. So there are various relaxations under this. I think one form was already introduced yesterday by HS Karthik in his talk. This is known as semi-device independence, where you place bound on your system. That is, if it is promised that your device is producing a qubit, then it should produce a qubit of dimension 2. Then post-quantum cryptography. So I haven't worked much on these, so I cannot give you like details, but you can really look up them. So I just want to tell this for the sake of completeness. So these are theories like beyond quantum theory, and people try to here look at Eve, who is beyond quantum theory, who is much more powerful, and then can one achieve security. Then there are quantum resistant or quantum proof or quantum safe. This is very common and is all over the internet, and you see these words very often. But what they mean is that if in the future one has access to a quantum computer, then do we discard all our classical cryptographic protocols, or are there some protocols which exist which can still be used to provide security in the presence of a quantum computer? So this is one area which looks at these protocols. Again, you can find a lot of material on the internet. Yeah, this is counterfactual quantum cryptography. I did some work on this with Professor R. Shrikant, I think, who will be speaking in one of the next webinars. So here, this is a little different from the usual cryptographic scenario. It's very counterintuitive, and it's conceptually challenging to understand. The idea here is just to give you a quick overview. The idea here is that you have an interferometer setup. This is a Michelson interferometer, but you could even have a Alexander interferometer. So there is Alice here who fires photons from her source. It hits the beam splitter, and the photon can either travel here or here. This is the external arm to Bob. So the idea here is that Alice and Bob share a secure secret bit value or a key only when the photon is restricted to this arm within the Alice station and it has never left her Alice station. So this is counterfactual, okay? So Alice and Bob share a secret key only in the cases when a photon has not traveled from Alice to Bob. This is so counterintuitive to what we have seen in BB84 now, where a photonic state or a photon travels from Alice to Bob, and then you end up with a key. So yes, other important things that are happening is space QKD. So initial days of QKD, terrestrial networks were exploited, like fiber optic communication networks were exploited. But as you progress, huge amount of area on huge kilometers of area on the earth has to be covered. If one has to realize the idea of quantum internet, there several users across the globe have to be connected. So scaling large distances is required, and this is a limitation because there are significant losses after 100 kilometers, and quantum repeaters, which are kind of amplifiers, are still in their are still have to be developed, much more for them to be realized physically. So people started looking at space networks or constellation of satellites to cover larger distances because the loss experience is very less. So putting compact quantum science into space, support for supporting next generation internet, is something which a large community of researchers are looking at. Here satellites are trusted network nodes. So there are like 4 configurations: downlink, where the source is placed on the satellite and this photon is beamed down to the detector on the ground; and uplink, where the source is on the ground and the satellite is moving, and when the satellite is exactly above this source, one has to fire a photon; entanglement distribution, where the satellite has to be in the right position to fire 2 photons, entangled photons, to ground stations; and then you have the satellite communication, where 2 satellites can establish quantum communication. This has not yet been realized, but all the other 3 links have been realized experimentally. like mostly by China. And some challenges that I want to mention this because this is a major part of my work in ICTQT in Poland is especially with respect to space QKD is entanglement, realizing entanglement sources for space communication. Because when you place these entanglement sources on satellites, there are a lot of considerations like temperature stabilizations, because the source is very sensitive to temperature, and its output, that is the production of photons, is very much dependent on this. And there are other considerations with respect to detectors, the kind of electronics that to go, the software that goes into it have to be coded differently, the radiation shield. So there are a lot of people working on like other aspects. And yeah, how to realize QKD protocols efficiently in broad daylight, because in broad daylight there is a lot of background noise. How to like separate them from your actual signal noise. These are some of the works that are going around. Some realization of satellite based QKD are, this is by China, like they distributed photon pairs or entanglement at a distance of 1200 kilometer, 500 kilometer above ground. And this is the article which gives you details about it. And here this is a CubeSat. This is by Singapore. So this is a low Earth orbit satellite where each cube is a 10 centimeter by say 10 centimeter unit, and this is a 3U satellite because there are 3 units. And here you can see this source which is on the right side, which is like placed. So miniaturization is also something which is very important because you don't want to send heavy payload into space. Yeah, so this is from the Singapore group, and in the Indian context, you have RRI and ISRO who have been collaborating to realize space QKD, and this is their article. So please look up. There are like several things. Finally, I would like to summarize by saying that today we have focused on the basics of QKD, not quantum cryptography, a small part of cryptography. And quantum cryptography or QKD involves a lot of classical processing. Mostly the problems which people are talking about in quantum cryptography are engineering problems and practical realizations. So one is also looking at improving security, because there are some technological limitations which we are facing now, but wisdom for this has to be still drawn from foundations, and insights into foundations also can be gained via security, because security and fundamental aspects of quantum foundations, they go hand in hand, contrary to what people think normally. Quantum internet requires development of both ground and space networks. So the future is both terrestrial and space networks working in tandem. So there is already a small demonstration of this by the Chinese team in China, where they have, I think it's called as the backbone network, the terrestrial network from Beijing and Shanghai, which is also connected to the space network. And finally, one other recent thing happening in crypto is impact of machine learning on security, finance, cyber security, and people are slowly beginning to applications of machine learning for cryptography. So with this, I would like to thank you for your attention, and if you have some questions, I'm open to answering.
Dr. Akshata, really it was a very insightful and scholastic talk. I'm sure all the participants would have got a lot of take-home message from your talk. Some UG students also have joined from Bijapur and other places.
Uh-huh.
And for them, uh, please tell them how cryptography applications could help in different fields in a few words.
Yes. So they are useful in, for example, cyber security. I see a related question here. Are symmetric crypto systems classical or quantum? No, symmetric crypto systems are classical, but to solve this problem of key distribution, we use the quantum way. Okay. Yeah, and to answer your question, Professor Ramesh, how is quantum cryptography useful? Right now, it is used in gaming. And to tell you, like my previous boss and the current boss of HS Karthik, he has this random number generator and this QKD kit,
Hi,
which
madam.
has been uh,
Hi, madam.
which
Thank
has
you, madam. Very well.
been used in Chile, which has been actively used in Chile for gambling purposes and some gaming purposes. Yeah, and then in Geneva, they have used these quantum cryptography. They have actually used the BB84 protocol itself for securely transmitting votes from one point to another point. So when we were in Geneva, so there is another nearby city, Lausanne. So I think they transmitted securely this voting system from one point to another. So yes, it has been implemented. So I think this also answers this cryptography where it is used. But to tell you, recently it is also being used for like online security. Okay, but of course, like I said, classical and quantum are both going hand in hand. There is another question here. What is the motivation for formulating these four requirements for key distribution? I think this is a question from Usha ma'am. I think she is asking about these assumptions
Yeah,
because look,
sorry.
yeah. So I
When
think
you posted it, I just thought of these maybe from classical cryptography. I thought the requirements come from classical cryptography. So you wanted, for completeness sake, you might have mentioned it.
yes, but no, because these
Okay.
are something which can never be relaxed, right? So the first
Right.
thing is
No,
you
I
the
thought it
theory
is
has
classical. Okay,
okay,
fine. Go ahead.
yeah. So ma'am, it is like if Eve is in your look, if you are typing some message, if somebody is looking over your shoulder, then there is no point in talking about security. So it comes from this.
Right.
And the other things, you are right, it comes from classical. But the quantum random number generator, this is a condition of quantum cryptography itself, because you see we are using this basis randomly. So and the final key comes because of joint action of Alice and Bob. So you need a true source of randomness. Otherwise, Eve can recognize some pattern, and then we can do a cryptanalysis easily with even a classical computer, I think.
Okay.
What is the meaning of universal quantum copier? Okay, by universal, I mean that it doesn't matter what quantum state you put, whether you put a zero state, that is in terms of polarization, linear, circular, right circular, it should copy it uniformly. Okay. Again, to give you the example in terms of classical, so the contents of your paper or the language with which this document is written, your copier should not care what it is, and it should copy it faithfully. Universal implies not specific to input
This is
state.
my
Yeah,
answer.
yeah, that is right, ma'am, you have already answered. Thank you for that. Break symmetric crypto systems, no, they cannot. That is precisely this is by Miss Girija, I think. Could quantum computers break crypto systems? No, they wouldn't. So that is why if there is a quantum computer, we would like to use symmetric crypto systems, but the only catch is that you need to use your secret key only once. Repeated use of secret key is not allowed. And then even I think a normal classical computer itself can do a cryptanalysis of this and then break. What are the
There is one
uses of
question from
yes,
ma'am.
please go ahead, sir.
After that, I will ask that question.
Okay, sorry. I'm just reading from the chat, sir. Please give me some time.
Yes.
So, what are the uses for cryptography in nanotechnology? Okay, I don't know for cryptography in nanotechnology, but I know vice versa. In cryptography, you need like quantum memories. So, quantum nanotechnology, there are some materials which are very useful. For example, memory. You see that there is Eve and Bob and Alice who need to have quantum memory at some point for different protocols. So these quantum memories should be able to hold your quantum states for a long time. So there are some metamaterials or nanomaterials which are very useful. So I am sure nanotechnology is useful. But one thing about cryptography is that there are some quantum effects which you see in nano devices, which actually could compromise the physical security of some cryptographic protocols. Okay, and one more thing, cryptography I think also it is useful in architecture, like nanotechnology architecture is like very useful for realization of physical platforms for cryptography. Then how quantum information is encrypted and processed, and how give output from the input. Okay, how it is encrypted? Sir, it is not encrypted. In classical, it is encrypted because you have a message and then you are putting some key and making it unintelligible, or in putting it in a form which cannot be recognized easily. So this is encryption. In quantum cryptography, we encode. We are not sending the actual message. There are protocols by which you can encrypt. Today we have not seen it. So we encrypted this in these protocols by using these base states X and Z, and we choose them randomly. But for today's protocol, we just encoded. That is, we put these photons in certain states, and at the end we ended up with a classical bit string which can be later used for classical encryption, and then you ensure your security. So I think somebody was asking a question. So
No, that was the
please.
only, ma'am. That question was asked in the YouTube channel, so I posted here.
Oh,
So all the
thank you, sir.
questions have
Thank
been
you for
answered.
that.
Thank you, thank you.
Thank you, sir.
So any other questions? We can take it up. Otherwise, you can ask Srinath sir or other senior members of our conference.
Somebody has
Srinath here.
posted one more question.
I just want to know
Sorry, sir. Please go ahead.
this entangled photon source availability, like it is now available in market, is what I understand. Can you just throw some
Yes,
light
sir.
on it?
Yes, sir. They are available. So depending on what is your requirement, for example, I can tell you, like for quantum, not only quantum, classical communication, there are two wavelengths which are called as telecom wavelengths, which are 1550 nanometer and 800 or nanometer. So at both these wavelengths, there are like proper sources which can produce you the entanglement sources. So there are various platforms, like the most common platform is this spontaneous down converted sources. For space applications, there are other considerations that this should be like high output sources, and temperature modeling is also one thing. But yes, of course, they are available, and most of the sources that are available are spontaneous down converted sources at
thank you.
1550.
I
Hello, sir.
understand that is not available in Indian market. Maybe in future, how it is made available so that the colleges or any other institutions can build up. Maybe in that direction you can throw some light.
Okay, sir. I will answer this
Hello.
question. Actually, it is very
Sure.
expensive to buy these sources,
sir.
as you rightly pointed out. But I think it is better to build these sources. Like I showed you in the last part of my talk, for this, we have been working on this space application. So to put a source into space, what are the considerations? So we did most part of the coding there, but there are experimentalists. There are very few experimentalists in the world who know how to build these sources, be it for land applications or space applications. So I would suggest it is better to build these sources in India. It is possible, and then probably like distribute them to colleges, because these are expensive. I don't know how would you want to make it economical for college students. But there should be an easier way of doing this, because or maybe you could try to find some crystals which, like BBO crystal, which is not so expensive compared to the space applications one, and then colleges or some expert from the quantum community group should go there and set it up for them. I think I would suggest not to buy them, but just build them here. It's possible to do it.
Thank you.
There is a question here. Can you answer me again? Which type of material is used for cryptography in nanotechnology? I think they are metamaterials. I'm sorry, I'm not an expert on them. But with respect to memory, they are metamaterials. But one example Yesterday I think HS Karthik gave in his talk like PT symmetric systems. There can be like some arresting of evolution also. With respect to the sources, there is silicon, there is lithium niobate also, which can be used to build sources. But yeah, I don't think I have more information on this. I am so sorry, because this is a very hardware and a very nanotechnology expertise question. Sorry about it. So how could consumer level OTP plus QKD over the internet be practical? Consumer level OTP. Okay, I think we wouldn't want to use directly the quantum wave for OTP, but what we could do is exchange keys by using BB84, copy these keys, save it locally on our classical computers, and then when a consumer level OTP has to be generated, let the service provider generate you a random OTP, and you also have your local key which has been generated by BB84. Somehow they should be used, like a protocol to authenticate that it has really the source is you. Okay, this is one way which you can do. This is something like normal classical protocols do. Like when you enter a password, it also verifies the MAC address of your laptop or your IP address of your internet. This could be something like this. And to give you an example about this OTP, please, for more information, look up this Samsung Quantum 4 by Samsung Quantum 4 phones, okay, where they have incorporated a quantum random number generator into a Samsung phone. I don't think they do an OTP, but I think they do a quantum safe internet protocol. So kindly take a look at this for more information. And also there is, I think, some attempts by Professor CM Chandrasekhar in IASC in this regard with respect to OTP. But I am not sure if it is running a quantum protocol to do that, because I'm yet to see this device. But this is just come out. He has completed this work, and I am sorry I can't give you more information because I don't have it. But yeah, this is my answer for now. Thank you.
Madam, before concluding,
Yes, sir.
one of the question is, what are the main limitations faced by current quantum cryptographic technologies for its advancement? What are
The
the
main,
limitations?
yes. So the main limit is loss, dealing with loss, because look, quantum cryptography cannot be just done between few kilometers. Okay, we have to, it has to be like how classical internet works. We have to cover the entire globe, service providers across the globe to connect. So for this, noise is one big limiting parameter. That is why people are looking at space, and we do not yet have a good physical realization of a quantum repeater. Okay, these are some kind of amplifiers, but not exactly. Classical amplifiers are present, so after a few kilometers of noise, signal can be boosted and then transmission can happen. But this is a difficulty with respect to quantum computers. Storing of large number of qubits for further processing, so we need huge amount of quantum memory. And to implement quantum measurements, large amount of quantum measurements, you need quantum computers, so it is also dependent on that. Then there are, on a quantum internet, you need sensors for sensing applications. So it's really, there are a lot of interconnections. That is why still, and then there are material limitations. Okay, there are material limitations. I think material scientists can, like, there has to be progress in terms of finding better exotic materials so that you can still push the limits. Okay, yeah, so this is my quick answer.
Cost.
Yes, cost. Yes, exactly, it's very expensive right now.
Thank you very much for an excellent presentation. I'm sure all the participants would have got a lot of information from your talk. There are many senior academicians and researchers who have joined for this webinar. On behalf of KSTA and all those who have joined from Cisco WebEx and YouTube platform, I'm very thankful to them. And the webinar is graced by our KSTA expert committee chair, Dr. Usha Madam. Madam, thank you very much for joining the webinar. We have with us expert committee members, Dr. Srinath, Dr. Sudha, Dr. Anant Nayak. For all of you, we are grateful to you for your time. And also we have senior most professor from Mysore University, Dr. Malesh sir. Thank you, sir. Dr. Sangeeta, Dr. Yashoda, Dr. Girija, Dr. Vinay, Dr. Pandurangappa, Dr. Madhu, Dr. Pradeep, Dr. Kantraju, and also our expert committee member, Dr. Karthik is there with us. Yesterday, he gave an excellent talk. I think Usha Madam was not there yesterday. In fact, yesterday's talk was also very informative. And we have Dr. Soumya, Dr. Moisin Taj, Dr. Trilok Chandran, Dr. Arvind Kulkarni, Dr. Abhishek, Dr. Girish. For all of you, thank you very much. Dr. Zina is also there. Thank you very much. Today we are concluding the third day session by Dr. Akshata Shenoy. And tomorrow we'll be having a talk by Dr. R. Prabhu. He is from IIT Dharwad. So I request all of you to join by 15. We'll be speaking on a few things about quantum systems. And day after tomorrow, we'll be having a talk by Senior Professor Dr. Sudha Madam on quantum science and technology, a bird's eye view on origin and development. The KSTA has been organizing such webinars mainly to give importance for the understanding of these new subjects by our students and teaching faculty. And in the coming days, quantum technology is going to have will be very important emerging technology which will be used in every field that you can imagine. That's why these series of webinars will be very useful for students and teaching faculty. In the coming days, KSTA will also organize offline talks at KSTA. With this, I thank you all for being with us and also our expert committee members. Thank you.
Thank you. Bye.
Thank you very much, sir. Thank you, madam. Thank you, one and all.
Bye, guys.